Hello, my name's David Garman. I'm Director of Research and Development at Plazer LLC. Today I'm going to be talking to you about non-thermal plasmas. I'm going to tell you where they come from, a little bit about their history, what they are, and how they can be used. So, what is a non-thermal plasma? Basically, it's lightning. If you can put lightning in a box or a discharge, then you can do all sorts of things, because the properties of lightning are very, very special. The first plasmas were developed around 1790s, and those were able to produce nanoparticles of silver. And since then, there's been many developments, and these include getting a definition of plasma, which really is an electrical discharge, sometimes stabilized by magnetic fields. So what can plasmas do? Plasmas are responsible for the formation of the amino acids, which were the building blocks of life. Plasmas can destroy chemicals. Plasmas can make difficult chemical reactions very simple. When you treat water with it, they can keep fruit and vegetables fresh, and they can clean surfaces. You can also destroy resistant bacteria, viruses, and funguses. So basically, they are very powerful operations. And the photograph on the right is actually of the plasma we produce. So how are they used? You can modify surfaces. You can remove complex organics, including forever chemicals. You can get rid of that, disinfect things very, very quickly without using other chemicals. You can remove hardness. You can get residual chemicals in water. And you can remove biofilms. So a plasma consists, in a very simple, by this cartoon. What it does, it shows you that if you have an electrode with a discharge, you get little lines of electrical conductivity. This creates electrons, it creates metal ions, it gives you hydrogen and many activated species. It also gives you cavitation bubbles and shock waves. In other words, you can think of it as the fourth state of matter. The fourth state of matter is not gas, it's not liquid, it's not solid, and in fact is that plasma. So the components of a plasma reactions, as we illustrated before, were the electrical discharge, electrons, ultraviolet radiation, pressure waves, free radicals. Sometimes you get instantaneous heating, you get ultrasonic effects, and the cavitation. In other words, we've got a lot of reactions going on all at the same time. So the question is, how much energy does it take? Are plasmas ready for industry? What happens in terms of long-term operation? Can we keep using them in a proper process? Can we minimize the chemical inputs which are required? What's the throughput capacity? And what happens if you've got solids or other complex chemicals present? We've got answers to those. Basically, plasmas are already in use. They're used for generating ozone. Microwave generators can also produce plasmas. Sonication is a very simple version of a plasma. Ultraviolet generators and catalytic systems also can use plasmas in various sorts. So we know about them, but these are using only simple components of a plasma rather than the full plasma. So to make things work on a industrial basis, we've got to have multiple electrodes or multiple discharges. It's got to be a high rate because we need to process a lot at any one time. It's got to be able to keep going at a sufficient rate to make things really happen on a consistent basis. And you've got to be able to deal with solids. Not absolutely essential, but it's good if you can. The electrodes have got to be stable, and because you're going to keep using them and reusing them. It's got to be robust construction. It can't be a simple glass jar. It's got to be something which can be made of stainless steel or some other robust material. It's got to be cheap to install, and it's got to have electrical controls and cooling controls as well if we're going to make it work. And finally, it's got to have a small footprint, something which you can easily place in another plant and use the existing equipment, because a plasma reactor is the reactor. It is not the whole process. It needs other things to help it. So as I've already mentioned, ozone reactors and generators are already in use. And there's lots of people who are working in this area, and many universities have got patents of various sorts. And many of them have also been trying to scale this up so you can get a big throughput. Most of them have been unsuccessful, or some of the other criteria we mentioned earlier are just simply not working. Well, now I want to introduce you to the Plazer equipment. The Plazer equipment is small. It's less than half a container. It's easy installation. It's almost plug and play. It's low energy. It's made of stainless steel or other forms of steel. It's light, relatively light. It is robust, and of course is made in the USA. And on the right you can see a picture of one of our dual reactor systems, which has already been set up and being used at a farm in Wisconsin. So earlier I mentioned this plasma system. And what is it? It's basically a simple tubular reactor. It discharges at several thousand discharges per second. It's got a good throughput of around 15 cubic meters an hour. It will take solids. It takes saline and non-saline waters. It's low energy. You can put multiple units together. And finally, it's fast. Most reactions are completed in under 2 seconds. This means we've met all those criteria I set out earlier in terms of being a viable commercial reactor. But having got that, how and where do you use it? Well, let's think what it does. We take the plasma, it produces electrons, it gives you water, salts, gases, neutral molecules. You've got solid particles in there which can be bacteria, fungus, or just simply lumps of metal or earth. It then goes through and it reacts with all the components of the plasma. You can produce nanoparticles, you kill all your organisms, and we get simple molecules which are readily available for bacteria in a digester example, or for other chemical reactions, or if you really want to treat it, you can take it right through to carbon dioxide and water. So there's many applications. You can use it for domestic wastewater. You can use it for industrial wastewater, complex ones with lots of organic chemicals. You can reuse water. Grey water is particularly good for that. You can process biosolids, break them down, and they are then easily dewatered. You can use it in the paper industry, in landfill leachates to remove all the heavy metals. And more importantly, but many of our concerns today, we can use it for some of these forever chemicals and trace pharmaceuticals, which are now becoming prevalent in all our waters, whether they're wastewater or fresh water. So one aspect I want to talk to you about is the effect of plasma activated water, PEAW or POR, and how that has an impact on fruit and vegetable and cleaning. So this simple picture tells you that what we can do is to use it for fruit and vegetables. You can use it for meat and seafood. You can use it for other complex biochemical reactions. But in the simplest way, we could take vegetables, wash them with pour, and get bacterial-free vegetables. It will also keep them fresher, and you can also use it for actually producing those vegetables as well. This is not just conjecture. There's over 150 scientific peer-reviewed papers which tell you all about this and show you how effective this is in this almost wonder water. You can use it in the dairy industry. You can improve the methane production, for example, from manure. You can treat the H2S, which comes off from that, and turn that into water and sulfur. You can treat the water which is left over and reuse it for technical water. The solids which come out of that are in two forms. You can use them as fertilizer, or you can use them as compost, and they are stable. You don't need to go through a big stabilization process. And finally, you can feed the plasma-activated water to cows. And what we have shown already is that you can get increased milk production. So this makes you think, well, how can this lead to better, more sustainable production overall? Well, if we think of putting a plasma or Plazer unit in the center of all this process, whether it's chemical, raw materials, waste disposal, or production of units, suddenly we're using a low energy, high intensity reaction which can lead to complete recycle. We are moving closer and closer to being able to get sustainable production. So let me just sum this up. Plasma systems offer farming and industry significant advantages in treatment and operation. Secondly, plasmas are already being used in all sorts of things, in the food industry for cleaning, but plasmas produced in the Plazer equipment is the first commercial unit for water and wastewater applications and for other large-scale industrial applications. Intensive non-thermal plasmas have the potential to assist with sustainable systems production, and the whole basis of this means that it is potentially a new industry technology base which is going to change the world. I'd like to say, if it's Plazer processed, then it's going to be part of the new revolution of sustainable operations.